Good afternoon, student. I welcome you all in this special session of chemical kinetics. Today I am going to discuss on a very simple subject, that is unimolecular theory or theories of unimolecular reactions. Now the title of my today's discussion is Unimolecular Reaction Revisited, because you are all aware of this unimolecular theory, but I will give special emphasis on the first theory or the cornerstone of this unimolecular reaction, that is Lindmann theory to Hinsel-Wood theory. I am planning to divide my lecture into two parts. In first part, I will discuss and derive the most simple theory, that is called the Lindmann theory, and in second part, I will discuss the Hinsel-Wood theory. Now, one thing is very important, because if you see your course content, you have to study 4 theories, starting from Lindmann to final theory you all know, which is a very, very important theory, that is called the RRKM theory, Rice, Ramsperger, Castle and Marcus theory. And in order to derive correctly RRK theory or RRKM theory, you must understand the Lindmann theory. So therefore, as I have already told you that it is the first theory and is the starting point of the unimolecular theory, and this theory are of paramount importance in chemical kinetics for clear-cut understanding of unimolecular reactions. And the pioneering work of F. L. Lindmann, who is a physicist, German-born British scientist, and he actually initiated this theory in 1921 or 1922. And there are some problems, and this Lindmann theory is elaborated by another great scientist. He is a Nobel laureate, Professor Hinsel-Wood. And so in second part, I will discuss this Hinsel-Wood theory, but there is a very good correlation between the Lindmann theory as well as the Hinsel-Wood theory. Now, as you know that if I am talking about the bimolecular reaction, so there is no problem. But if I am talking about the unimolecular reaction, here I am giving some of the very important simple unimolecular reactions. And you will find that the dissociation of the bromine or isomerization of the acetonitrile or the decomposition of sulfuryl chloride, or very common example, many gaseous reactions. And another is the conversion of the cyclopropane to propene, like that. So if it is a bimolecular reaction, and you know that for any type of the reaction, collision is very important. So if there is 2 molecules, so there is no problem. You come closer and just collides, bond breaking and bond making process. But if it is a unimolecular reaction and there is only one molecule, so how that particular molecule acquired energy? That is the very important question. And Lindmann tried to solve this equation, and there was a meeting of Faraday Society, and that time it was observed that this type of reaction is based on the radiation hypothesis. Suppose if we take a vessel and there is a molecule, so if we increase the heat, so with the help of the radiation, that reaction occurs, and that was developed by another scientist. His name is Perrin. But during this conversation of this trans-Faraday society, Lindmann objected this theory and he proposed a new theory to solve that radiation hypothesis, and therefore, and then of course he published a paper in 1922. I will show you that paper also. And in the same time, actually he presented his presentation in, I think, September 1921, and another scientist, his name is J.A. Christensen, he also submitted his PhD thesis in University of Copenhagen in 1921. Although he has studied some reaction of hydrogen-halogen reaction, bromine decomposition reaction, but ultimately that is also related to the unimolecular theory. So in some books, you will find that this Lindmann unimolecular theory can be recognized as Lindmann-Christensen theory. And as I have already told you, the most important point is that if it is a unimolecular reaction, so only A is converted into B or A is converted into product. So where does the energy come from? Of course, collision is very, very important. Now this is the, you can see it here. This is the original research paper of Professor Lindmann, and as I have already told you that it is published in Trans-Faraday Society, and I am taken from the internet. It is available in this thing. And you see the discussion on the radiation theory of the chemical reactions, and the Arnias was there, Langmuir was there, Professor Einardhar was there, Perrin was there. So this is the first paper of this great Professor Lindmann. And when I will discuss the theory of insolute theory, I will also discuss this thing. So in 1927 also, he published a paper, that is Proceeding of the Royal Society, 1927, and he elaborated that unimolecular theory. So therefore this theory is also very important, because what is the difference between the Lindmann theory and insolute theory? In Lindmann theory, generally we consider for the collision, but how that energy is distributed, that is developed by the insolute. And as I told you that he was awarded the Nobel Prize in the chemistry for chemical reaction in the year of 1956, jointly with another Russian scientist, Simonov. So let me start with that first theory, that is the Lindmann theory, and it is very simple. Any student can solve it without any problem. First, we will use a steady state approximation method, and of course they observed the pressure dependence of the rate law. When I derive, you will see that if at very high pressure the reaction is first order, but if the pressure is low, it becomes second order. Why? Because there is only one molecule. So how it is second order? That is the problem. And what is the reason for the transition from the second order to first order kinetics? That is the problem. So if I see the system, I can write so there is only one molecule and for collision we need another molecule. So the first step is pre-equilibrium step, and in some book you will find that this is the inert gas, or you can write M also, no problem. And this you can write rate constant K1. So first there is a collision, and this process is called the energization process. Don't get confused with the activated process. It is called the energized process after the collision. This is the energized species that were additional energy. Now there is a second step that is called the de-energization process. That means that excited molecule having energy, it releases some energy and is converted into again, so that part is A inverse 1. And finally, so there is a time lag which is very important. There is a time lag between the energization process and the de-energization process. And then of course, this is, I'll now derive this thing. So it is converted into product. So with the help of this simple mechanism, we can derive the equation. Now I am coming to the derivation part. Now, as you know, that is a very, very elementary information about this Lindmann theory, and most of the, you will get it, most of the physical chemistry book, this derivation is available. But frankly speaking, that I am taking most of the important information from a very popular book, that is Chemical Kinetics, 3rd edition by Ledler, and I have also taken some information from the Atkins physical chemistry. It is also available in the book of Levine physical chemistry as well as Barrow physical chemistry, this derivation. But why it is important? Because it is the starting point of unimolecular reaction. Therefore, you have to understand this Lindmann theory. Now I am coming to the derivation. Just remove it. So very simple derivation is there. I can write like that. A, you can write M or you can write A, K1, A star and A. And second step is very simple, that A star is converted into product, is K2. As you know that if I want to calculate the rate of first order, so I can write subscript. This indicates the first order unimolecular, first order rate constant for the unimolecular reaction is related, depends upon the A. This is normal cases. But as I have already told you that the derivation first part is the applying the steady state approximation method, and this is the pre-equilibrium, is the first step, it is the slow step. So what I can write, rate is equal to K2 and A star. It is a rate determining step. So it is very simple. I have to determine A star from this equation, applying steady state approximation. You know all these things. I have already, I'm not going into details because it is very simple. What is important? Pressure dependency is important. Therefore, I am just dealing with all these things. So I can write E by dt of A star, very simple, is equal to A1 A square, don't get excited, very simple, minus A inverse 1 A star A, and last stage is minus A2 A star. Yes, because we are considering the steady state, so you know that this part we assume 0. So what I can write like that, A1 A square is equal to, I can write A star A inverse 1 A plus A2. So therefore A star is equal to A1 A square divided by A plus K2. Okay. So I can substitute this value. So rate is equal to K2 K1, simple thing, A square. Now, you know that, as I have already discussed, that if the pressure is very high, what happened? That the de-energization process, because it is converted into energized process, pressure is very high, that it will release that energy. So it is converted into again the original condition. And sometimes we can use some inert gas for that, for collision purpose. So what happened? This K inverse 1 is greater than this K2. This is greater than this K2, because more and more de-energization process. So I can eliminate, so K2 K1 A square K inverse 1 A. So I use some red color, this A is cancelled. So I am getting K2 or K1, K2, you can write like that. K inverse 1 and A. So if I write this K2, K inverse 1 is K infinite. So it is K infinite A. What does it mean? That is at high pressure, the reaction obeys the first order kinetics. That is the first observation of the Lindmann. And he has used large number of reaction. On contrary, in one case pressure is very high, second case pressure is very low. Low pressure. Because most of the time it's a gaseous reaction, concentration you can also call it. In that case, this K2 process, then the product formation is high. So therefore, I can eliminate this K. So I will get K2, K1, A square divided by K2. So again this K2 can be cancelled. So it is K1 A square. It is second order kinetics. Because now this is the question. Because this is, you are talking about the unimolecular Lindmann theory. So why such? So it is pressure dependent. In the high pressure, it is first order. But how it is second order? Because it is the unimolecular type of the reaction. So the last part is you have to determine the okay, I can so what I am getting K1 rate is the last step A. Okay, and second case what I am getting rate is equal to K1 K2 A square divided by, I think, what is that thing? Getting plus K2. So now last part is that the determination of unimolecular rate constant. In some books also you can write like that. K uni you can also write like that. K observed you can write. So there is no up to you. So now if I just equate these two equations, I will get K1 A, please look it very carefully, the last step equal to K1 K2 A square K inverse 1 A plus K2. So I can write like that. So if I plot a graph between K1 and the concentration of A, I'll show you that graph also later on. It's a hyperbola type of thing. And if I just rearrange this equation, both numerator and denominator is divided by K inverse 1A. So what I will get? I will get K1, K2, K inverse 1A A divided by this divided by, so it is 1 plus K2 K inverse 1A. So this A cancel. So what I am getting, A1 K inverse 1 A2 divided by 1 plus A2 K inverse 1A. This I can call it K infinite, I can also call it K infinite. So again, we are not getting straight line, and this there is a fall off, that is called the K infinite. You know, there is a flat, that is called, and low pressure, low concentration, so it is called the fall off. So how do I get the K1 value? So the last part is there. Last part is there. So if I just reverse it, so 1 divided by K1, I just, just reverse it. So it is K inverse 1, K1, K2 plus 1 divided by K1A. Please see it very carefully, this reaction. I've done nothing, just reverse it. So if it is Y, it is X. So now if I plot, I will show you, plot a graph 1 divided by K1 and 1 by A. So ideal condition is that there must be a state. So it is a theoretical part. In order to determine the first order rate constant for the unimolecular reaction, there must be a state line. But unfortunately, we are getting, I'll show you such type of things. So why such things is happened? So that is the difference between this experimental as well as the observed value. So by that method, we can calculate the K. Now I'll show you the actual picture. Just come to the. So what I have derived, this thing. We have already seen this thing, that K1, K infinite means K1, K2 divided by and 1 plus K2, K inverse 1. So it is actually K1, K inverse 1 and K2. So I can write this K infinite. And this part is so the experimental verification of this thing. So you see this first case, that when you plot a graph between K1, K of that, this is actually, you can call it, and simply A concentration. So such type of thing is observed. So it is called the fall off. And he could not explain this reason, why such type of thing is happened. And then if I just reverse that reaction, as I have already told you, that if I just reverse it like that, so K1, K1, K2. I am already told you 1 divided by K1A is equal to 1 by K1. I have already shown it. So it will get. Ideal condition is that it must be a straight line. It is a theoretical part. But again, the problem is that when he performs some of the experiment, he is getting such type of path. So that means there is some problem, deviation from the linearity. So he could not explain. He published this paper in 1922, and then Hinshelwood elaborated this theory and explained this behavior. In next lecture, I will discuss all these things. So I can call what is the limitation of the Lindmann theory. First thing is that yes, it is true that it is the starting point of any unimolecular reaction. So it was the starting point, but it is not the perfect. There are certain problems. Number one is does not explain the energy distribution, because of course if I write like that, you all know these things. K is equal to Z E divided by KT, or RT conductance in terms of molecules. So it is a collision theory. So yes, there is a collision, and due to this collision, and there is the energy, the number of binary collisions. But how that, because there are many degrees of freedom, so one molecule absorb energy, then it transfer to another energy, like that. So Lindmann could not explain this energy distribution. And in order to understand the energy distribution, we have to take the help of statistical thermodynamics or statistical mechanics, probability. And of course, Hinshelwood proposed the refined or elaborated theory, and he accounted for the distribution of the energy among vibrational modes. So therefore, in the second part, we will discuss this Hinshelwood theory. And of course, there was some problem because Hinshelwood only used the statistical mechanics. And there is no concept of the quantum mechanical calculation. So again, there is a modification, and that is called the RRK theory, Rice, Ramsperger, and the Cassel theory. That is the theory number 3rd. So let me summarize the things. Again, I am just tell you that unimolecular Lindmann theory is the first theory, and Lindmann is a great scientist. Of course, he is a physicist, and ultimately he joined in the cabinet of Winston Churchill. That is another story. But he proposed a temperature dependence of the unimolecular rate constant. And the observation is that at very high pressure, it is of course first order, but in low pressure, it is second order. And when you plot a graph between 1 inverse K unimolecular 1 by S, so there is no straight line is observed. So in my next part, I will discuss the Hinshelwood theory. Thank you very much.